We're going to shift gears here now, everyone. I'm going to take you guys back to grade 1. Who can tell me what 3 plus 4 is? 7. It's an easy question, right? 3 plus 4 is equal to 7 if you're adding scalars together. It always is if you're adding scalars. And in grade 1, that's exactly what you did, is added scalars. Now, your teacher didn't tell you you were adding scalars. Your teacher may not have even known you were adding scalars. But that's exactly what you were doing in grade 1. 3 plus 4 always equals 7. However, if you're adding vectors together, 3 plus 4 isn't always equal to 7. It could be. 3 to the east plus 4 to the east is equal to 7 to the east, right? But what if you're saying 3 to the east plus 4 to the west? What is it? 1 to the west. So 3 plus 4 is equal to 1 in that case, right? What if you're saying 4 to the west, 4 to the east and 3 to the west? Well, then 4 plus 3 is equal to 1 to the east in that case. So 4 plus 3 isn't always equal to 7. It is if you're adding scalars, but not if you're adding vectors. You guys learned adding vectors in one dimension, probably in grade 5 or grade 6. Probably grade 6, I would think. Where you're adding negative numbers, right? So we've done that before as well. That's not new either. But what if you're adding 3 to the east, 4 to the north? What's the sum of those vectors then? 3 plus 4 doesn't equal 7. 3 plus 4 doesn't equal 1 or minus 1. 3 plus 4 equals 5 in that case. Today we're going to learn how to add vectors together when we're adding them in 2 dimensions. A horizontal dimension, an east-west direction, and a vertical dimension, a north-south dimension. So the normal rules of addition do not apply, or not necessarily at least. 3 plus 4 might equal 7, depending upon the directions. But because we do have to pay attention to direction, it's not always going to be equal to 7. In the end, when we're adding vectors in 2 dimensions together, right, 3 plus 4, 3 to the east, 4 to the north, we have to get ultimately a vector diagram that ends up being a right angle triangle, and then we're going to use some trigonometry. Some of you may have caught that. When I said 3 plus 4 is equal to 5, some of you may remember from math class that the hypotenuse of a triangle that has 3 on one side and 4 on the other side is 5. Right? 3 squared plus 4 squared equals 5 squared. Anybody remember that one? Okay. That's not one that you have to know, right? It's just one that sometimes you remember it, right? So if you knew that, then you probably thought somewhere in your mind, oh, wait a second, we're going to do some trigonometry here, some Pythagorean Theorem here, some right angle triangle stuff here. And we are. It's exactly what we're going to do with this. The goal is to get a vector diagram that's a right angle triangle, and then do some mathematics. To get a vector diagram, we have to follow certain rules. Okay, and you guys have never really had to follow these rules before because you've never really drawn a vector diagram. The first rule is this. You're going to draw your vector as a line segment. So if it's 3 to the east, you're going to draw it like this, with a little arrow on the end of it showing direction. If it's 3 to the north, you're going to draw it like this. 3 to the west, like this. 3 to the south, like this. You're going to draw a little line segment with an arrow on the end of it. That's easy. That's the easy part. There's no vector diagram here yet. There's just a vector. Well, then we're going to draw another one. So if we have 3 to the east, let's say we got 3 to the east here, and we've got 4 to the north, well, now we have 2 vectors drawn, right? But the key here is this. When you draw those 2 vectors together, when you add those 2 vectors together, we're going to draw them front to back. Sometimes we call it head to tail. Front to back. We can't draw it like this, because that's drawn front to front. We can't draw it like this, because that's drawn back to back. Okay, we can draw it like this. 3 plus 4 is equal to whatever right here, because that's drawn front to back. Or we could draw it like this. 4 plus 3 is equal to whatever, because that's also drawn front to back. So draw a vector that it's a line segment with an arrow on the end of it. Draw another one that's a line segment with the arrow on the end of it. And then put them together so that it's front to back. Let's go back to the one dimension again for a second. 3 plus 4 is equal to 7. Well, here we're going to say 4 plus 3 is equal to, what's this? Well, the hypotenuse. So we have to figure that one out, right? The sum of the vectors, which is really what we're trying to find here, right? We're talking about a sum. We're talking about adding things together. The sum of these vectors, sometimes we call it the resultant vector, should be drawn backwards. It's back to front. So my blue vectors here, these are the ones that I'm adding together, are drawn front to back. My resultant vector right here, that's the sum of all the vectors. When I add them together, that's what I get. The resultant vector is drawn back to front. Or sometimes we say it's drawn from start to finish. So there's your vector diagram. Now what do you do with it? Okay, I drew this. This is technically a vector diagram right here. I drew this. I added them together, and I get 7. So I can do that, right? When I draw this, how do I add these ones together? Let's do a couple examples, and we'll see how we're going to combine these, okay? How we're going to actually do the mathematics of it. Let's do the first one. Okay, let's do one at a time. 10 meters north and 20 meters north. That's an easy vector diagram, right? 10 meters to the north. 20 meters to the north. We'll draw the 20 meters to the north twice as long as the 10 meters to the north, right? Because it is. The resultant vector, we'll draw this one in red, goes from start to finish. Okay, that's easy, right? 10 plus 10 north, 20 to the north equals 30 meters to the north. Okay, easy one, easy one. Next one, 10 meters to the north and 20 meters to the south. Okay, this one's a little bit harder. 10 meters to the north, 20 meters to the south, right? Drawn front to back. See that? Front to back there. The resultant vector is drawn from start to finish or back to front. So the resultant vector will be drawn right there in red. What's the number for that going to be? 10 to the north plus 20 to the south gives me 10 meters to the south, right? Easy enough. Now let's do it in 2 dimensions. 10 to the north, 20 to the east. 10 to the north. Let's see here. Here's 10 to the north. 20 to the east. Here's 20 to the east. Can I draw the 20 to the east right here? Does that work? Not allowed to do that. Why not? What was that rule of vector addition? We have to draw it front to back. This is drawn back to back, right? Back of one vector to back of the next vector. It's not what I want. I got a couple of options here. I could draw it like this, 10 plus 20, or I could draw it like this, 20 plus 10. In both cases, it's drawn front to back or front to back. Either way is good. As long as it's drawn front to back, either way is good. Now the resultant vector, the red vector, goes from start to finish or from back to front. The value of that resultant we can find by using what? A grade 9 math thing. What is it? The Pythagorean Theorem. Right. Let's get rid of this so we got a little bit more space here. The Pythagorean Theorem says a squared plus b squared is equal to c squared. So we're going to say r squared is equal to 10 squared plus 20 squared. Or r is equal to the square root of 10 squared plus 20 squared. That's the square root of 500 if you do the math there. and the square root of 500 is going to be somewhere in the range of about 23-ish, I think. 22.36. Now, you can see that if we drew it the second way, we'd get the same answer, right? It would still be 10 squared plus 20 squared square rooted. We'd still get 22 meters regardless of which diagram you drew. Does that make sense? So in this case, 10 plus 20 doesn't equal 30. It doesn't equal 10. 10 plus 20 equals 22 because our directions are different. Yep. Yeah, that's a good question. Because resultant vector is a vector, direction is important. We're not going to worry about that right now, though, okay? There is a direction, and we do eventually have to include that. But right now, we're going to focus on just the magnitude of it. It's a good question, though. Just not going to answer it yet. Let's do the last one here. 10 meters to the west and 20 meters to the south. 10 meters to the west is this way. 20 meters to the south is this way. Where do we draw it? 20 meters to the south like this. Is that okay? Is that okay, James? Is that okay? No? What's wrong with it? Yeah. We've got it drawn back to back. It needs to be back to front or front to back, however you want to say it. So we've got a couple of options here. We can draw it this way. Notice my 20 meter vector is about twice as long as my 10 meter vector. Okay, we always want to draw it roughly to scale here. That's right. Okay, front to back there. We could have also drawn it like this. That's also drawn front to back, right? Both of those work. Where does my resultant go? Clearly, it's going to go right here, right? But you always want to draw an arrow on the end of it because it's a vector. Where should the arrow go? Up here or down here? The red vector, the resultant vector, should always go back to front or backwards. Right? If it was front to back, okay, this one should go, I said back to front, it shouldn't go, it should go front to front. Okay, the arrow should go in front to front. It's from start to finish. Make sense? Similarly over here, it's going front to front as well, from start to finish. You can find R here. In fact, you already have. The magnitude of the resultant vector is, once again, square root of 10 squared plus 20 squared, square root of 500 gives me 22 meters. So once again, the magnitude of that is equal to 22 meters. Is that okay? Well, look at that. Now we know how to add. It took you till you were what? How old are you guys? 16, most of you guys? Took you till you were 16 to learn how to add completely. Well, still, you still haven't really learned to add completely yet because we'll do a little bit more when you've got angles that aren't north and east, but angles that are at 22 degrees south of west or something like that. We just won't do that today. You're getting there, though. You're getting there. You can almost add now. What do we do when we add more than two vectors? What's 1 plus 2 plus 3 if we're adding scalars? That should be an easy question for us, I hope, right? What's 1 plus 2 plus 3? What is it? Say 8? 6. No. That's okay. That's okay. 1 plus 2 plus 3 is equal to 6. If we're adding scalars. If we're adding vectors, it could be, but not necessarily. It could be 4, it could be any one of a number of combinations. If we're adding them in 2 dimensions, it could be even trickier. If we're adding 3 vectors together in 2 dimensions, then we've still got to follow our rules of drawing vector diagrams. The only problem is we don't get a right-angled triangle out of it right away. 25 meters to the north plus 20 meters to the east plus 30 meters to the north. Let's draw this out. 25 meters north. 20 meters east. Hey, is that okay so far? I'm not done, right, because I've got 3 vectors. But so far, am I good here? Are these drawn front to back? Yeah, so that's good so far. Then we got another 30 meters to the north. Is that okay? my resultant vector should go from start to finish. Let's draw the next one while we're at it, okay? We won't worry about solving it quite yet. Let's just draw the next one. 10 meters to the east. Okay, let's say 10 meters to the east. 15 to the south. Okay, so far so good because I'm drawing it front to back. 12 meters to the west. We're going over here now. Also front to back. 20 meters to the south. Is that good? Sure, they're all drawn front to back, except that resultant vector, which should go here, from start to finish. How do you how do you calculate the length of that red line now? How do you calculate the sum of all of these vectors when you don't have a triangle? Remember what we said the goal was? The goal is to always get a vector diagram that is a right-angled triangle. These are all right angles, but it's not a triangle. So let's do some components here. Let's do the first one. You guys have probably learned this in math class, right? This is your x-axis, this is your y-axis. You guys seen that? You guys know what I'm talking about there, right? X-axis and y-axis, x, y, right here. Let's look at all of these vectors. We're doing the first one there. Let's add up all of the x's, and then we'll add up all the y's. How much of that 25 is x? How much of that 25 is on this axis? Right? How much of that 25 meters right there is like this? The 25 meters we have right here, how much of that number is going horizontal like this? Zero, none. How much of the 20 meters, the next vector, is on the x-axis? How much of that one is on the x-axis? 20. How much of this one is on the x-axis? 0, because it's all y, right? Let's add them up. Okay, now we're going to do y's, the y-axis. How much of that 25 is on the y-axis? 25. How much of that 20 is on the y-axis? How much of that 20 is up and down? 0, because it's all on the x-axis. It's all horizontal. The 30 is all of it. Let's add these up. We get 55 meters. Now, here's the crux of it. Let's redraw it. We had 3 vectors added together. We've just changed it to 2 vectors. A 20 meter to the east and a 55 meter to the north. We know how to find this because we got a right angle triangle, right? We can do the Pythagorean Theorem. We can say r squared is equal to, what was that? 20. R squared is equal to 20 squared plus 55 squared, or r is equal to the square root of 20 squared plus 55 squared, whatever that works out to be. Yep. Yep. So we've just actually gone through quite a little bit of stuff here, right? We've learned how to add vectors together in essence, right? We have to draw a vector diagram. We have to get a right angle triangle as part of that vector diagram. Okay, to do the vector diagram, the vectors that we're adding together must be drawn front to back, okay? Arrow to back, arrow to tail, head to tail, sometimes they call it. Okay, and then the resultant vector, we usually draw it in red, has to be drawn from start to finish. So we learned to do that here when we have 2 vectors that we're adding together. Okay, one's 10 to the north, 20 to the east, looks something like this. Do the Pythagorean Theorem to find the value of r. But when we have 3 vectors, it's a little bit trickier. Because remember the goal? We want to find a right angle triangle. Well, we don't have one here. Right? We don't have a right angle triangle here. So we got to get one. To get one, we break it into x's and y's. Take the x of each of them. 0, 20, 0 for the x components. Add them together. For the y components, 25, 0, 30. Add them up. Now we've got 2 vectors instead of 3. Instead of adding 25 to 20 to 30, we're adding 20 to 55. Now we've got a right angle triangle. Now we can do the Pythagorean theorem. So what's the difference between this question that we just did and this question right here? This stuff is the difference. Okay, in the last page, we went straight from the question to the right angle triangle. In this question, we had to go through this process first, the x's and the y's. Does that make sense? Okay. I'm going to have you work on this one right now. 10 plus 15 to the south, 12 to the west, 20 to the south, and then we'll wrap it up after you're done that question, okay? All right, let's take a look at it here now, guys. You know that you have to break it up into x's and y's because you don't have a simple right angle triangle here. If we did, great. Do the Pythagorean theorem, done. We don't, so we got to get one. Let's add up all the x's first here. First one, how much of that 10 meters is x? How much of it's horizontal? All of it, right? All of it is. So let's put in 10 meters. How much of that 15 meters, this one right here, is horizontal? 15? Is the answer 15 there? How much of that 15 is this way? None of it. It's all this way, right? It's all down. So we're going to say that the second one is 0. Third one, how much of that 12 is x? Here's a tough one, actually. Who thinks they have the answer to that? What is it? Negative 12. Why negative? It's to the west. It's backwards. And the last one, none of it is east-west. All of it is north-south. Now let's add these up. We end up getting negative 2. Now let's do the y component. None of the first one is the y component. All 10 of it is x. 15 of the second one is y component. Is that right? Not quite. Not quite. Should be negative 15 because it's down. 0 of the next one. And negative 20 for the next one. Gives me negative 35. Now we can redraw it as a right angle triangle. Now somebody asked me a great question as you were working on this. He said, how do we know which way to draw the arrows in our second diagram, the one that we draw now? How do we know which way to draw it? Well, negative 2 on the x component means 2 to the west. So let's draw 2 to the west. Negative 35 means 35 to the south. So the resultant vector should look something like this. Does that make sense? Anybody draw it like this? Anybody draw like that? Is there a difference? Is one right and one wrong? No, they're both right. As long as you draw it front to back, it's right. So now let's figure out what the value of r is. Say r squared is equal to 35 squared plus 2 squared. R is therefore the square root of that. What do we end up getting there? 35.1 meters. Now remember, there is a direction to find as well. We're just not worrying about that today, okay? I want to focus on just the magnitude today. Who feels reasonably comfortable with that? Good, good. We'll pick it up there tomorrow. We'll do some more work with vectors and go from there.